let's go ahead and get started. So, all right. So we've talked a little bit, well, last time we finished up on our circuit optimization with Verilog. I'm going to leave that section like that. I will question you about K-maps on your midterm final, and you will see a K-map on your senior exam. That is your warning.
Yay.
So make sure you understand how K-maps work and how to do basic circuit optimization, because you will probably see that. And by probably, I mean definitely.
Yay.
Yeah,
okay.
Do we know the date for that yet?
Nope.
Great.
So, we talked about low level. We're going to come with the circuitry. We're now just going to assume that Verilog can take care of changing all our gates into something that's efficient and layout, so forth and so on. So we're going to actually start talking more a little higher level with the architecture. So the first thing we're going to do is we're going to come up with our first basic processor design with a simple finite state machine using the example of a vending machine, like to get a Coke. And we're going to then explain the problems with that and why.
Coke?
Like Coke.
No. No pop. Let's get like.
Wait, what's that word you used?
Pop?
Pop.
What's that?
He's from South.
I agree
I know
with Coke.
you're not from the South, are you?
Yes.
Nope.
Okay.
I
Maybe you should
agree
go
with
back out. So.
We'll get some tea for you. It's okay.
Yeah. So we're going to talk about our first
nasty.
basic processor design, very basic, and then we're going to essentially determine that that is not a good design and why we need to go into something that's programmable.
Did you get a water out of the vending machine?
A water, yeah. I never understood that. Bottled water. I'm like, you can go to
Just
any
wait, it
faucet.
gets better. They've invented this like pouch for it, so it's gonna be like you're drinking a water droplet,
Oh,
and
that's
it's like an
good.
edible
There's
pouch
no-
and everything, and it's so much better for everything than
Okay.
plastic.
50 years down the road, we'll be taking air.
First thing,
Buying air.
there are two different types of processors. Actually, there's many different types, but I'm going to go and show you two. There's a general purpose, and that's the kind you usually see inside of laptops, on your phone, et cetera, et cetera. General purpose, it's there to solve any problem that you
General
give
stuff.
it. General stuff. Special purpose,
Whoa.
these definitely do exist. Necessary for application with non-standard requirements. Maybe you need very high performance regular tasks. So an example here is your graphics card is a special processor. It's not general purpose. It doesn't accept interrupts, or really can't run an operating system, at least not that I'm aware of yet. But since it's tuned to graphics or performance, they can actually produce a very powerful chip that does a specific task quickly. Another example is low power or low cost. Okay, this is in your watch. Wait, we don't have wristwatches anymore, do we?
You got the Apple Watch.
Right, so you have a digital one. Yeah, it's considered a processor in there because it's changing. Very basic one, very special purpose. But its advantage is it's extremely low power. The battery probably lasts longer than your phone, right? I'm assuming.
Lasts longer than you.
Yeah, in some situations. But of course, it can't run an operating system. It really can only do one thing, but it does its one thing well and doesn't consume power.
What would the processor in an Apple Watch be considered?
So Apple Watch, last I looked, it did have a general purpose chip in there. It was just a very low power general purpose one, because it's running a very basic OS or type software on it.
Super tiny.
Super tiny. In your car, for example, the computer that computes basically the fuel mixture, air fuel mixture, simple computer, very special purpose, very low power. Of course, it has also the requirements of it needs to take a beating and keep on going because it's in a very rugged environment, so to speak. All right.
Poor chip.
Poor chip. Yeah, no. Now we're talking about processors' feelings. Okay, so we're going to focus on special purpose or a special purpose controller. We're going to talk about the design of a non-programmable controller. We're going to implement it from components we've used from previous lectures. And then next we're going to talk about a general purpose one because we're going to show why special purpose in most cases is not a good choice.
Wait, we're actually going to use the stuff we learned?
Yeah. Okay, simple device. Hey, look at that. When was the last time you seen that?
Not like that.
Not like that, no. Not like that anymore. But I think it's a pretty good example.
I'm trying to figure out the sodas on there.
There's a Coke.
Oh, I guess y'all haven't.
Pepsi. It's
Yeah,
both.
there's the Coke.
Is that
There's
RC?
That looks
right
like
here.
a
Yeah.
cream soda or something.
I didn't
Way
think they make
or-
RC
Top
anymore.
left.
They
No,
make
it's a
all of them.
Pepsi in a bottle.
All right.
Top left?
So let's
Yeah.
just say they've given us the task of building a custom controller for a vending machine. All right. We could use a general processor, but let's save some money with a custom controller. So how's this work? We give it coins. Yeah, I know, coins, not bills. No bills.
What about credit card?
What?
What?
Downstairs.
It does take credit card?
Yeah.
Are you serious?
Yeah, you didn't know that?
Well, you can see how often I go to vending machine. Wow.
Drink your tea in your office.
Out of
Look,
his
I was
Mario mug.
I was sad when it took a quarter to buy a drink, but oh well. All right, input and output.
At least it was only
now
a
it
quarter.
costs so
I don't
much.
even
That's
know.
$1.25.
I'm not even want to know. Coin trigger. You know, you put in a coin, it triggers. Hey, look, they put in a coin.
I mean, you can't pull it out with a string.
You could try. Refund button, because obviously if they want a refund from they put in some coins and went, oops, I only have 2 instead of 3. They want to get their 2 coins back.
I don't think
Makes
it's
them
actually putting out the button.
Is it not a button anymore?
No,
No, your
like the
arrow's
coin
not
slot's
pointing at it.
sideways, and the button's like right here, and it's pointing at like the little rectangle below that,
Where you get your
where you
No,
get
that's
the
not the
coins
button.
out from.
No, that's a button. The coins come out
Sure.
from. Whatever. All right.
Whatever.
10
Only
drink
10
selectors.
selections?
Yeah.
Only 10.
First world problems. First world problems. 10 pressure sensors. What are those? Ooh.
The buttons.
No.
No?
Tell you
Oh.
if there's actually a drink there or not, right? Because you don't want them to say, "Give me a Coke," and then nothing comes out, and then it takes their money. Wouldn't be good.
But it still does that sometimes.
You punch the machine.
So we need to design ours so it doesn't do that.
Yeah.
All right. What's its output?
A drink
A drink.
and change if necessary.
10 drink. Yeah. Release latches. 1 for each drink, of course, to open it up. And then a refund coin latch. See, the refunds are down here in the blackness that you
I
can't
have
see.
never seen a rectangular refund button. I've always seen a little circle button right beside
All right, so I'm showing my age. Fine. You remember these? You remember the machines that look like that?
Yeah.
Yeah. All right.
Are you trying to call him
You
old?
can always make it so much simpler when you just say, look, press the selection, we'll dispense the Coke. If you get, we'll dispense the drink. If you get the drink, please put money in. And that when then once you put money in, we'll say, okay, we've dispensed 1 Coke, and so they'll.
Oh wow, it's going by itself. That's amazing. So we're going to accept quarters only. We're going to say they're 75 cents.
Oh my gosh.
What?
It's just going back to.
I know,
You
it's
already
crazy.
said
Once we
that.
get the money, they can select a drink. I thought I was going to say once we get the money, we never ever give it back.
Yes.
If they want a refund, release the coins inserted. Okay. And we'll say that we have the mechanical hardware for that. We need to write the controller that makes all these decisions and makes it happen.
Right.
Magic.
Hey, I can't go forward.
Auto
It
magically.
broke.
It broke. It does that a lot.
I see that.
Oh, because
We don't want no free drinks and no stealing money.
Oh.
Darn.
We don't want them to steal money. Okay, so we need a state because we need to know how many coins have been inserted. All right. We're going to use something called read-only memory that's going to define outputs and state transitions via ROM. So I'm going to talk about that. And that's going to define, how do you go from one state to another. And then, custom combinatorial circuits to actually figure out where to do what. All right, finite state machines. We were going to go through the mathematical explanation of this, which you probably will hopefully do in algorithms. But, yay. I needed more enthusiasm. Like, yeah, algorithms. Algorithms is fun, okay?
Who teaches it?
Right now, Bubba Tunde. So it has different states, aka, in our example, how many coins have been inserted. Inputs, are they hitting the refund button? Are they hitting a drink selector? I want to say, are they kicking it, but we don't care about that. And then outputs, give them a drink, which drink to give them, which money. So those are the, you have states and inputs and outputs, and then you have a transition function that if you're in a current state and you have a current state, current input, which output do you go to? Okay? That's how we define this mathematically. Mapping each current to next, and then the output function. Oh, this is how you go from one state to another, and then you have another function for how you get what outputs come from it. So one function from you have this state, this input, what's the next input or next state you go to, and then another function that you have states and input, what output do you produce? 2 common state machines. I'm not going to test you over these names, but do keep in mind that a Moore machine is based on the current state only. It doesn't take into account the input, while a Mealy machine is based on the current state and current input. So which one are we? Mealy, right. All right, so finite state machine for vending machine. So you have 0 coins, 1 coin, 2 coins, 3 coins. So if we're at 0, we start at 0, right?
Yeah.
All right, so if they put in a coin, where do we go?
Fun.
Oh man, that's amazing. Coin trigger for 2, 3, and then we'll say that if they put in another coin, we just dump all the coins and go back to 0. Sure, whatever.
Why not?
Trying to make this easy. They can
One
figure it
at a
out.
time.
If at any point they hit the refund button on 1, 2, and 3, it goes back to 0 coins, right? Because they've been refunded. If they select a drink while having 3 coins, we're going to go back to 0 coins. These are all the state transitions.
This looks like a graph.
Yeah, that's what I was
from
thinking
data
too.
structures.
Yeah, it's a graph from data structures. You got it. But we're not going to have to do it in a JC list or a JC matrix. That's way too much work.
I was going to say, it reminded me of system analysis.
You'd what?
I hate
Drop
system
that.
analysis.
No.
That's what it's
Let's do it.
Yeah.
In hardware, you ready?
Yep.
Hmm.
No.
Whoever said no, smart. Why would we not want to do that in hardware?
Because we're not hardware people.
Wow. It'd be way too slow.
Fair point.
And if they ran out of a specific drink, we just go back to 3 coins and wait
Yeah,
for them
this
to make
is
another
totally
selection.
system analysis.
I hate system analysis.
We can make a great graph exactly like that.
We'll see how we're pulling it all together.
I know, but I didn't like that class. So
Yeah,
I don't like this part.
It's a graph. You like graphs, right?
Eh.
All right.
Pictures are nice.
All right, here's another picture. This is a little counterintuitive for some of y'all because the inputs are coming from the right and the outputs are to the left. Just work with it. So, transition functions, you have your inputs, coin trigger, and then your current state. There's only 1 coin selected. The next tells you what your next state's going to be, and then of course what your output is. Do you actually produce a drink, or do you refund them? So, example, your current state is 1 coin. The input is coin trigger. They put in a coin. Your next state is 2 coins, and your output is nothing. If your current state was 3 coins and your input was drink select, next state would be 0 coins. Output would be drink release. 2-bit state. Ooh, what are those?
What?
What are these?
Processors.
No.
No.
Flip
Oh,
flops.
so, yeah, that's
Yeah.
a flip flop.
They're flip flops. So we need 2 flip flops in order to represent 2 bits.
Does he have 2?
One for each.
Nice. All right, so I think we've talked about the state and how the state is going to hold how many coins we have. So next comes a read-only memory. Array of memory values that are constant, non-volatile. We'll show, well, right. So there's 2 different kinds of memories. You have the read-only and the programmable. Well, programmable read-only can only be written exactly once. We're not going to go into exactly how the programmable ones are created. I'm just going to show you how the regular ROMs are created. I hope we get to the picture. Okay, we'll do this. Sure. So here's our truth table. Remember, like I said, if you write out the truth table, you're going to get the answer. So here we start. Over here is your current state. Coin trigger, drink select, refund button. So if you have no coins, no one does a coin trigger, no drink select, no refund, your next state is of course 0, 0, and you don't release a coin and you don't release a drink. Right. Again, if you're in that state but they hit refund, you can release the coins, but luckily there's no coins to release, so we're good. They do a drink select, we do nothing. They're trying to steal a drink. Too bad.
Rude.
Yeah, exactly. Rude. All right. 0, 0. They put in a coin. Our next state is, of course, 1 coin. We don't do a coin release or a drink release yet. They only have 1 coin. All right. We're going to kind of skip a couple. You have 1 coin. They put in another coin. Next state is 2 because I have 2. Again, don't coin release. Don't do a drink release. And then was another coin. Next state is 3. Again, don't do anything. You have 3. They do a drink select. You give them the drink. You go back to 0. You see what this is doing? The important part here is notice that everything has now been reduced to 0 and 1, which means we can represent it with a wire with either low voltage or high voltage. All right. Sure. Thanks. So, how are we going to do this? Well,
That wasn't all the inputs though, was it?
no.
Because
You want to
left
go?
off
You want to
the
write the
one-
other 24?
What's that?
See 24 more entries. You want to fill them in?
Oh, okay, gotcha, okay, 'cause, yeah.
Anyone? No, I didn't think so.
Really?
No.
You
You good with this, Jonah? Okay, good. Well, Jonah, if Jonah's got it.
Yes, I'm great.
Ouch.
All right.
You catch it.
Hey, remember the decoder?
Hello.
Hey, sure.
Sure. Okay. What'd the decoder do?
Whatever you said.
What-
Decode stuff.
Yeah, whatever I said. All right.
I decode stuff.
What it does is, given the 3 wires of input, it's going to activate only 1 wire on the left. Okay? So if you have none of these are voltage, all these are low voltage, it'll activate 0. If just A sub 0 is activated, it'll activate 1. If A sub 1 is activated and A sub 0, it'll activate 3. It's just which line is it activating, aka sending high voltage down. That's what a decoder does. Okay. So from the decoder, we're going to send voltage down in one direction. The wires coming down are going to activate certain data lines. Those bits that I was telling you about in the truth table, that's what that's going to represent. When you activate a line, by default, these wires are not connected that are coming down. But if you want them to be connected, you use something called a diode, so that if voltage was coming down here, it would go down and activate this line. So you put diodes on your wires to activate certain lines. Let's do a quick example. So if you activate A sub 0 and A sub 1, that represents the value 3. So wire number 3, notice that's the 4th wire. Wire number 3 is activated, aka high voltage. The ones with the diodes on it will send it out to the data. So you can use this map to you can use this structure to map a certain input to activating certain lines. Okay? All right. Any questions on this?
Why does it say 8 entry 4-bit ROM?
8 entry.
Because there's 8.
No.
Oh, it's
Oh,
a.
it's the total value that you can enter. You can look at it from binary.
Right. So it's an 8 entry. Notice it's a 3x8 decoder.
Right.
So it can activate up to 8 lines. In order to activate up to 8 lines in a decoder, you need 3 coming in. It's a 4-bit ROM because there are final 4 bits.
Oh,
coming
okay,
out.
gotcha.
The 3 over here is just because it's an 8-bit decoder. If it was a 16-bit decoder, you'd need 4 lines. Good question. Any others? All right. Okay. So for our vending machine, let's actually think about it. We have 2 bits of state. We have 22 inputs. We have 10 drink selections, 10 input, 10 sensors, right? So that's 20 right there. A coin trigger and a refund button, so that's 22. So that would mean that our ROM would have 24-bit addresses coming out of its decoder, aka down here should have 24 lines coming out. All right. But if you think about that, if it's 24 coming out, oh wait, here we go.
Why are the, oh, because the 2 state bits, never mind.
Yeah, the 2 state bits, right, because we still have the 2 state bits. Because the idea is that these inputs are going to be fed into this decoder, which will then activate a certain line, and where 24 lines will eventually come back out. Let's see, so, oh, I'm sorry. 24 bits coming in, my apologies to the decoder. 13 bits coming out, I said that backwards. 24 bits are coming in to the decoder. 24 are coming in up here. But you only have 13 coming out. Why do you have 13 coming out? Because you have, again, you need to update your 2 state bits, and you have 11 outputs, which are, what would be 11?
The drinks and.
Oh yeah, the drink latch release, so there's 1 for each
Coin.
drink, so that's 10 right there. Then you have, the other output is your refund button? Yeah, your refund button. So there's 11 outputs plus 2 states, would be 13 bits of coming out of the decoder, of the ROM. So we need a 2 to the 24 entry 13-bit ROM, which would require
Oh gosh.
a lot of bits. Not acceptable. Especially if we're trying to build a cheap controller, that's not going to happen.
Nope.
Nope. So we already have a problem, and we were just trying to make things simple. So how can we reduce this? Well, replace the 10 selector inputs and 10 pressure inputs with a single input. Because in reality, we just want to know, did they hit the drink selection button? And then just have a couple of other logic behind the scene to fix up which one was actually selected later. So we just need to know drink selection. If you do that, then you have your two state bits plus 3 inputs. Refund, refund, your drink select, and a coin trigger. There we go. So those are your 3 inputs. So it's a 5-bit ROM address. Well, that's a lot easier going into that decoder. And then next state is just your next state, and then 2 control trigger bits, refund or give them the drink. And then we'll figure out which drink that was later. So it's 4-bit. So 2 to the 5th times 4 is 128-bit ROM. All right, that's pretty cheap. Y'all see what I'm doing here? Okay. So I'm putting it all together. Let's go ahead and take a moment to
Oh boy.
stare this all down. Oh man, wires that way. Right, Joan? Oh yeah, you get Joan. All right. So let's see. If they did, where's the coin trigger? That's over there on the bottom right. That's the
It's going
3rd
right
line
below.
into the decoder. Okay, great. Notice at the bottom 2 wires of the state machine. Great. And let's see. Refund for undo. And notice that we are ANDing the pressure sensor and the drink selector for an input. In other words,
Oh.
for them to select a drink, it also has to have a drink has to be there. Otherwise, we're not even sending it to the controller. So that simplifies our decoder a lot. That just goes into an input OR gate saying one of them's been selected, and then that's the 5th wire there. So you see how the decoder only gets 5 inputs, and the drink, if it does need to release a drink, notice a drink release in the upper right. That goes to a bunch of ANDs, so it's going to activate one line in all those ANDs, but the other one is going to be from the drink selector that came as a separate input. So they kind of bypassed having to put that input into our processor by just going around it.
Literally.
Literally going around it, yes. 2 bits. We got a coin release as well. Okay. Any questions about this one? No questions?
Okay, this one right now is, well, I press the drink selector button, right? The moment I do that, I send a signal.
If there's a drink there.
If there's a, well, no, if there's a drink there, there should already be a 1 on that line, right? Or a voltage on that
Well,
line.
yeah, there's voltage up here. If you hit that button, it has to also have voltage there for this AND to say
Right.
true, which goes into an OR gate, which obviously, if you once you activate an OR gate, it's going to send it to your decoder. Right.
Okay, now I'm going to the output, the drink release latches. I press the button. Okay, so I'm putting a drink selector in, I press the button. Is there a delay, or, because I'm pressing the button, do I have to keep the button closed in order, because it's still got to process all this stuff in the sender there.
Right. Well, it
before
has to go
send
through the
signal out.
decoder. It has to activate the line,
It goes
come back
super
out.
fast.
But yeah, that's pretty fast.
Instantaneous.
I mean, I don't even think would be slow enough to
Okay,
try and
just
trick
checking.
it here. You could try. There is some delay. That's correct, but it's pretty small.
Small enough to where if we're pressing the button, it has enough time.
And most people, when I send them to use a vending machine, I go, give it to me. Or, so eventually it'll work.
Yeah, but most of our machines don't do just regular buttons anymore.
And they don't even do buttons, they just have like a little.
Well,
They have a picture of it.
Yeah. They have a
You just
picture.
punch it, and it gives you this.
And
Oh,
it's
do you
like this
literally-
big square.
Mhm.
Yeah.
And it gives you
Or they got the
They
really
made it a
fancy
punching
ones where you have to type in like
A
A7 and it like goes over and like draws it out and then drops it.
Those are some fancy machines.
All right, so.
Now, if you look at the machines in Japan, those are even fancier.
So,
They give you warm food.
can anyone see an error or a problem?
It's a mess.
No, this is actually pretty straightforward.
My refund's an undo button.
No. What if
Reading
they
coins.
Huh?
Reading coins.
reading coins? Well, we assume that works. What if
How
they
do you
hit
know
a
it's
refund and
Canadian
a drink
dollars?
select at the same time?
Broken.
Does it give you the drink and your money back?
Well, it depends on which
Maybe.
one gets there first.
But, well, what if they both get there at the same time?
Then you got a problem. Your machine
The
froze.
machine would explode and freeze it.
Yeah.
Free sodas for all. Well, think about it. If both of these wires are high, then that's a separate. That's going to be a separate line that's activated on this decoder. So you just have to make sure that that line. What do we want it to do? Give them a drink, refund them, or ignore them?
Nothing.
Nothing. I just give them a drink because once you have their money, never let them. You never give it back. So, I'd give them a drink. Maybe you want to do nothing. Maybe you want to release the
Give them
coins.
the wrong drink.
Give them the wrong drink. Wow. Yeah, because that's the other problem.
Oh, that would be cool. Take the one that you've got the most of. Just say,
So
okay,
the
whichever one
refund
has
is
the
actually
most drinks,
pretty-
So give them that one.
So the refund actually that's fixable in this processor because we have a separate line for it. But what if they activate 2 drinks at the same time?
They're idiots. Oh, sorry.
Well, think about it.
Machine's preference.
Well, no. Well, what happens here? They activate these 2, right? It gets ORed into one line here, which activate the drink release, which activates the release for all these, but you're holding it down to release those 2 up here. So do you get 2 drinks? Yeah. Hmm.
That's a problem.
How do we fix that?
Yeah.
Yep.
Sydney, you were all excited about K-maps, and then we go over here, and now, what's wrong?
I'm tired.
Okay. How could we fix that? Think of it this way. What input to our processor is not what we want it to be?
The drink song.
The drink select. So can we somehow make that 0 if 2 or more are activated over here? Sure. How could we do that?
Not.
XOR?
Okay, so XOR would mean that, right, you would have to have an odd number selected. So I could select 3 at the same time, and then XOR would produce 1. Good guess. Yeah. Good.
You can see somebody up there just like.
Yeah, exactly. Yes.
Oh, let's see.
Trust people to not be jerks.
How well does that work out in real life?
Not very
Not a bit. You've worked in retail, haven't you?
Yes. People are jerks.
One of my first experiences going away to college, I come into some sort of dorm, these guys are around this vending machine, and it's the weekend. I didn't realize, I come there, I go to get some, so I can't get any, there's no drinks in there or whatever. They had poured salt water or whatever, or ice water in there, and they basically emptied the machine, because they triggered all the latches to release.
Mm-hmm. Okay.
So,
Smart.
I mean, we could try and, if we ANDed drink selection bits, those would only be high if you pressed 2 or more together. So you could, or AND all that, put into a separate OR, that would be a separate wire. And then you would have to, basically, you'd want to knot that, and then AND that output with this guy down here.
are we trying to keep the cost down?
Yeah. Well, I'm just saying, well, then you add more ANDs, but that's still cheaper than trying to make a gigantic decoder.
Yeah.
So we could fix that. All right, here's another one. What happens if we make the price $1? Oh!
Update your coin drive.
Update our coin drive.
Update
Because
it
you
to
have to
4
change the
instead of 3.
hardware, with the lines. For
Yeah, we have to change our hardware.
State.
It's no longer. Yeah, we must
I wish
redesign
they
the
just still
controller.
do.
We must add more state.
Oh yeah.
But a programmable processor only needs a software upgrade, right? So that would actually be advantageous in this situation. Also, do we really care about how much power this thing consumes?
Nope.
Not really. I mean, unless it
Not our
was like
problem.
supercomputer level or something, but it's not.
Not yet.
What do we need to do to allow other coins? Now we need separate coin triggers and logic to take care of that.
That's gross. Just use quarters.
And I already talked about 2 drinks at once. Yeah, just use quarters.
Just use quarters.
So,
none of the rest of the coins in the world matter. Just
So hopefully you can see if you make a simple finite state machine, you can solve a lot of these problems. But every time you want to make a change, you have to redesign your hardware. Right? Hence why we want our machines to be programmable. I got to stop here and make sure this is clear. Do y'all see why you want your machines to be programmable?
Yes,
It's
you don't-
probably intuitive to most pure scientists, but this is even just a simple basic example. Even with a vending machine, you want it to be programmable.
So you don't
for
have
change.
to change the hardware.
You don't have to change the hardware, which is expensive. All right. Everyone good with this presentation?
Imagine trying to change all the hardware and all the vending machines.
It'd be sadness.
Sadness, right?